new topic. It's about entropy. It's related to thermodynamics. Of course, thermodynamics is a very big part of physics. It's a very important part related to the theory of gas, theory of molecular motions in this room, and so on. But of course, we cannot go deeply in this. And I hope that I just transmit you the ideology of thermodynamics. Yeah, thermodynamics is a kind of house which we construct over the ground, which is statistical mechanics. So we have statistical mechanics, we have states of individual systems, so-called microstates, for example, position and momentum of molecule in this room, or atoms in this table, or in this table. But thermodynamics does not handle these microstates. It's not interested in velocity of individual particle or its position. It's handle macrostates. Macrostates is some collection of microstates, some, for example, some volume of gas. So, and the molecule in this volume of gas, they have microstates, but volume as whole has macrostate. A macrostate is described by such macro parameters as temperature. So temperature is not characteristics of one atom or one molecule. Temperature is characteristics of some macrostate, of some volume, volume and pressure. So these are characteristics of thermodynamics. Thermodynamics was created essentially due to efforts of German physicist Boltzmann. And maybe it's a good place to start this story. That Boltzmann, he was really treated very badly by many his contemporary scientists, especially by Mach. Mach was philosopher and physicist. And Mach, he developed in some way descriptive viewpoint on physics. That physics should describe only those quantities that we can measure and observe. In particular, at that time, at the time of Boltzmann, nobody was able to observe atoms. So atoms, but Boltzmann used them in his models. He needed some discrete quantities. So microstate is assigned to this small discrete body. And then he introduced macrostates, configurations of these microstates. But Mach wrote everywhere and in many speeches told that Boltzmann is really idiot. He discussed some mystical creatures, atoms, and nobody has seen these atoms. And it's not clear, only this was the reason for the death of Boltzmann. But Boltzmann finally made suicide, and this campaign, which was driven by Mach about these mystical atoms, which can be considered only by idiots who use in science quantities which are not observable. So it was no, it was not so good story, but it demonstrates how that sometimes people brain is much more powerful than experiment. At Boltzmann time, and maybe 50, maybe even more years after him, nobody was able to observe directly atoms. But mind of humans, of course, Boltzmann was not the first. Who was not the first who invented atoms. Plato was the first in ancient Greece who introduced atoms, and in this time struggle also was very intensive. Aristotle, who is famous, of course, but he was so strongly against Plato's atoms that he demanded from Greece authorities to put in fire all the books and writings of Plato. Okay, so it was history. Now we're going to this Boltzmann entropy. So we have lambda. This is collection of macrostates. Yeah. So these are subsets of this Z omega of or microstates. So element M1, M2, and so on. These are these subsets of this set. So omega is the set of all points, and its subsets, disjoint subsets, are macrostates. Then Boltzmann entropy is given by this formula, where n with index m is the number of microstates in the macrostate m. So roughly speaking, this is the number of the points, in this set. Boltzmann, this is Boltzmann constant. We are not interested in it in this very brief course. So Boltzmann entropy is increasing function of the size of macrostate. Larger macrostate, more points, more microstates in it. So larger this number, larger Boltzmann entropy. If size of macrostate increases, entropy is also increases. The biggest macrostate have the highest entropy. So in this biggest macrostate is called equilibrium. The system wants to approach macrostate because it's biggest equilibrium state, because it's biggest, and if point is moving, it's a higher probability to find it's inside this big set. So the most probable state is equilibrium state. So the largest, the biggest macrostate is the most probable. So this is textbook explanation of the second law of thermodynamics. So increasing of entropy makes system more and more uncertain because this set is very big. So if this macrostate is small, then of course let us make some picture. If macrostate is small, so this is all possible microstates, and for example, this is very small macrostate, and here is very big macrostate equilibrium. Yeah. So and now we have a point, our particle, which is moving overall. Then the probability that it is inside this set is higher than the probability that our point is inside this set. Yeah. So this is it's so often inside. So this is meaning of the. Oh, I destroyed this, but I hope that you have seen. Oh no, I did not destroy it. Yeah, so I put it here. So this is meaning of the second law of thermodynamics. That any system, isolated system, and this whole story was about isolated systems because otherwise there is some emission from this set and so on. In any isolated system, it has the tendency to make as uncertain as possible because the most big set of macrostates is the most probable, and the particle will spend the most time inside it. So particle with high probability is inside this big set. So and we don't know so much about this particle, where it is inside this big set. Yeah. So this is second law of thermodynamics, that entropy and disorder, because if you know that it's in a small set, we know everything about this particle. So we know its position, it is order. But when it's in big Z, we don't know so much about it. So it is disorder. So disorder is increasing. And this is irreversibility. It's very deep notion of the process for isolated system. So asymmetry between past and future. So of course, typically we introduce time as just mathematical parameter. It's mathematical parameter. But generally we need some quantity which describe this dynamics from past to future. And all classical systems have this parameter. This is parameter which determine error of time, which we go from the states of low entropy to the states of big entropy. Of course, this is not good story about the second law of thermodynamics, because any isolated system with time will become more and more disordered, and more or less this is death. Yeah, so, but of course there is no isolated system, and this is because each system is inside another and they're connected, but our whole universe, it is isolated system. if there is nothing outside the universe. So, and therefore entropy in the universe is increasing with each day, and soon or later our universe will die. Not because stars will finish their energy, but just because entropy will increase. So it was very short story about thermodynamics and very sad law, second law of thermodynamics. The law about increasing of entropy in classical isolated system. But in theory of information, people use Shannon entropy. It's defined in different way, but it's possible to prove some theorems connecting them. We have no time for this. So Shannon entropy is defined for probability distribution. So we have, for example, some quantity, and we have probabilities to get these values. For example, we have coin tossing, and one side takes probability 1/2, and another side have probability 1/2. Then it's calculated by this formula. This calculated by this formula. So if probability distribution is uniform, so for example, if there are n points, and if this is 1/n, then the entropy will be logarithm n. It will be very large. If this quantity is concentrated in 1 point, it can be even 0. So this is, more uncertainty, larger entropy. More uncertainty, larger entropy. So this is the same as for Boltzmann entropy. Now we go to quantum physics. Here the notion of entropy was introduced by von Neumann. And we have quantum system. We have its state rho, density operator. And von Neumann entropy is defined as trace of this operator, rho multiplied by logarithm rho. No, some people can become afraid, what is logarithm of matrix or of operator? Be not afraid, I shall explain soon. So how to calculate this von Neumann entropy? And it will be also needed in your home task. Since rho is Hermitian, there exists orthonormal basis consisting of eigenvectors. So these are such eigenbases. Because all density matrices are positive defined, all these numbers are non-negative. And since trace is 1, the sum is 1. So you find these numbers, and then this is just probability distribution, which was in Shannon entropy. And if you calculate this trace, we get precisely Shannon entropy. So this trace of this operator in this basis is precisely Shannon entropy, but only in this special basis, the basis of eigenvectors of density operator. This is rho. On this side is rho, here is PG, yeah. Only in this basis. What are properties? What are properties of von Neumann entropy? It is 0 if and only if rho is a pure state. So the pure state is the most ordered state. The class of pure states is the class of most ordered quantum states. Maximum entropy, and this you can calculate by yourself, is approached for this. It's approached for this density operator. So this is unit operator, and we want to have trace 1, so divided by n. So its entropy is logarithm n. Yeah. Now we studied Schrödinger dynamics. So if you have isolated quantum system and psi t is its pure state, its dynamics is described by Schrödinger equation, where h it should be calligraphic. It should be calligraphic here. Yeah. This is systems Hamiltonian. Yeah. So we can write a solution in this way, where this is exponent of the operator. Yeah. It is possible to derive, no, we shall not spend time for this, that if we have this dynamics for pure states, then for mixed states, for density operators, we have such dynamics. And this is commutator. This is our energy operator, Hamiltonian, and this is our density operator, rho. Commutator is the product h rho minus rho h. So this equation is called von Neumann equation. It's a very direct consequence of Schrödinger equation. And the main property of von Neumann entropy, of quantum entropy, that it's not changed in the process of such evolution. That entropy of rho t for any instant of time t is the same as von Neumann entropy of initial state. So in here we see the great difference between classical and quantum evolution. In classical case, entropy of isolated system can increase, and it should increase because of the second law of thermodynamics, up to maximal value. In quantum case, entropy of isolated system is preserved. So if quantum system is isolated, it preserves its order as long as possible. So there is no second law of entropy. Now we go to home task number 8. Consider the coin. Suppose that it's not here, so not 1/2, 1/2. Probability of one side is 6 and another side 1 minus 6. X is parameter between 0 and 1. Draw the graph, how entropy is changed when this X change from 0 to 1. Problem 2, we go to quantum mechanics and consider density matrix. I think it's density matrix. Yeah, 1 Hermitian, and it's positive, and 1 for, yeah, it's density operator. And we want to find von Neumann entropy of this state. How to do this? Use this method which we did before. Find its eigenvalues, find its I think we don't need even eigenvectors. It's enough to find eigenvalues, because in this basis of eigenvectors, the matrix has this form where these guys are just eigenvalues. So you need only eigenvalues. You need not eigenvectors. Of course, it's in basis of eigenvectors, but by themselves you need not calculate them. Now, more complicated density matrix, you have seen its ones. Alpha, beta, arbitrary complex numbers, such that the sum of their squares is 1. And we want to find the, again, von Neumann entropy of this state. It will do as in the previous case, find its eigenvalues, start to calculate, but then will be one difficulty. You will find such expression, 0 multiplied by logarithm 0. You can find its S limit, epsilon go to 0, epsilon logarithm epsilon. And if you recall the course of mathematical analysis and so-called L'Hopital rule, you can calculate that it is 0. So you will find that von Neumann entropy is 0 of this guy. Stop. Yeah, so we finish this. Stop.